practice, risk-based inspection, scope and references, and terms and definitions. In this module, we shall learn about intention and purpose of API 580, scope, references, terms, and definition. API 580 is a recommended practice and hence not mandatory. It's intended to complement the inspection codes for pressure vessel, piping, and storage tank, API 510, 570, and 653. API 580 also covers valves, heat exchangers, and rotating equipment, pumps, and compressor. The inspection codes API 510, 570, 653 calculates the time when half of the corrosion allowance still remains by the time the next inspection interval is due. This is called half-life rule. The inspection interval determined through API 580 is used as a comparison. Although API 580 is a recommended practice and cannot violate or overrule inspection codes which are mandatory, but all these inspection codes have provisions to make exception for RBI recommendation if it is based on sound judgment and good engineering practice. Therefore, RBI can be used to increase the inspection interval beyond the half-life rule set out by API 510, 570, and 653 inspection codes. API 580 defines the minimum requirement for an inspection program. And the main output of API 580 is the inspection program. The inspection program is a process that starts with identification and selection of equipment, screening, and prioritizing based on the level of risk, and preparation of inspection plan for each equipment, interval, type and extent of inspection and examination, and finally, inspection recommendations. Inspection program may also result in non-inspection recommendations such as repair, alteration, replacement, process change, the use of inhibitors, change of materials, and so forth. To prepare an inspection plan, first you need to identify the high-risk equipment and the risk drivers, parameters that have significant effect on increasing or decreasing the risk value. You should also identify the dominant damage mechanism that have the potential to cause failure, and accordingly select those inspection and examination methods and techniques that can adequately detect and monitor the size and location of such damages. This would help to reduce uncertainty, to plan repair and replacement, and maximize the reliability and life cycle of the equipment. API 580 links the inspection campaign to the damages and risk. By directing the inspection effort, the inspection activities on those areas that experience negligible deterioration could therefore be reduced or eliminated, while inspection efforts is concentrated on those areas that have higher risk of failure. Also, those inspection and examination methods that could not adequately capture the expected damage mechanism and deterioration could be replaced by more efficient methods and techniques. Normally, inspection cost and risk is reduced by implementing an RBI approach, although reducing inspection cost is not the primary object of RBI. On the other hand, it is the safety and integrity of the equipment that is the priority and objective of RBI. So this might be a potential exam question. What is the primary objective of RBI, which is integrity and safety of the equipment? And would say, or the other way, they might also ask, what is the byproduct of RBI? It would be reduction in inspection costs, because you're diverting the inspection efforts towards high-risk drivers and eliminating inspection efforts when there is not much benefit on it or it cannot detect the expected damage mechanism. RBI means risk prioritized inspection. So this can be also a potential question. So in RBI, the inspection is prioritized based on risk. So you have to read the other way around. inspection based on risk, IBR. RBI is a sound integrity plan if coupled with a management of change program, provided the equipment operating within the integrity operating window. So there is a clause here. RBI is not a solution for all. If the integrity operating window means that the range of operation for pressure, temperature, process is changed, is violated, then RBI is not the answer for that. Does not have an answer for that. RBI assessment includes considering the risk drivers, determining damage mechanism, as well as the extent, type, size, and location of these damages, selecting the most suitable inspection types and examination methods and techniques, determining the inspection and examination coverage and frequency, and lastly, determining the inspection interval. Considering other risk mitigating measures and determining the residual risk if the inspection plan and recommendations were implemented. The output of RBI assessment is the inspection plan. So what is the output of RBI assessment? It's the inspection plan plus non-inspection recommendations. A repair, replacement, alteration, process change, use of inhibitors, and so forth. To assess the probability of failure, we should consider all possible damage mechanisms. API 580 reiterates that no book, including this recommended practice, could substitute the experience and sound judgment of qualified inspectors and engineers. So this is a guideline, and it cannot be replaced by actually on-the-field experience, especially considering that each case might be different from other cases. The purpose of RBI is intended to provide minimum requirements for developing, implementing, maintaining an RBI program. So that's the purpose of this document, the minimum requirements for developing, implementing, and maintaining an RBI program, and guide the owner user in developing and implementing an inspection plan. RBI emphasizes safe and reliable operation through risk prioritized inspection. So this sentence, there's a lot of meaning in it. Firstly, the purpose is safe and reliable operation. And how he does that? Through inspection by prioritizing risk. Risk prioritized inspection. RBI should go through the following 12 steps. Understand what are design assumptions, input, envelope, plan how to carry the RBI assessment based on a particular equipment. Are you going to do qualitative assessment, quantitative, or semi-quantitative? Semi-quantitative is the most popular one because it uses the speed and expertise of subject matter experts like corrosion specialists, operation personnel, and inspectors, while purely quantitative is too consuming, costly, and so the semi-quantitative use the speed and expertise of qualitative method plus the logic and detail of quantitative method, because you're not looking for absolute risk. There's no point. Firstly, it's not possible to get the absolute risk value or eliminate the risk totally for that purpose. And secondly, you're looking for relative risk. So as long as the risk is acceptable beyond you can live with it, that's it. So hence semi-quantitative. Qualitative purely can be used when screening and trying to find out the high-risk drivers or critical equipment. So then collect all the data, construction data, including design calculations. Fourth, inspection, examination, and testing reports, and perform a data validation. So you first get all the data. Manufacturer record book, design calculation, inspection reports, any report from the maintenance and operation. First get the facts and figures on the table, because the more facts and figures you have on the table, the better you can decide. This is for every situation. And then do a data validation, whether this data you have, how much you can trust this data, how accurate this data are. So that's called data validation. So you sort of cross-check with other data. There are different methods. We can't go into detail on this, but you're practically trying to understand whether this data is correct and how reliable is this data. So by cross-checking, for example, if you have a pressure increase because of temperature increase, so that looks normal because the pressure increases with temperature, or vice versa. But if you have a pressure increase but the temperature, you see the data is decreasing, so there should be something else here. So this data might not be valid, or there is some other issue here you have. So I've identified the potential damage mechanism, damage pattern. So try to find the pattern, location, type, size of discontinuities encountered on expected based on the service history, previous experience, publication, consultation with engineer and corrosion specialists, as well as other relevant personnel, operation, maintenance. So all the available knowledge, whether it's in the form of publication, whether it is in the form of repair history, service history, and based on your previous experience or other people, experts' previous experience, such as engineers, corrosion specialists, operation and maintenance people, that could help a lot to direct you to divert you to the right direction when you are evaluating or assessing equipment. Assign a degree of severity, maximum damage limit, or acceptance criteria for each possible damage mechanism. So once you know what sort of damages you might expect, so each one you should assign whether that damage lead to, say, a small leak or a large leak or explosion or a fire. So the consequence you have to assign to that, because you want to by assigning a consequence of failure for each potential damage mechanism, and then you got the probability of failure, how likely it is that particular damage mechanism could lead to failure. So by multiplying these two, and how likely it is that that damage mechanism would end to such a consequence, or that scenario, that's consequence of failure. Eventually the product of these two, the likelihood of these two, the probability of failure happening as a result of that particular damage mechanism, and the consequence happening or predicted based on that damage mechanism, you can find the risk, because it's a product of probability of failure and consequence of failure, and outline your recommendations, solution plan, how to manage the risk. Either monitor it until it comes to a critical stage where the risk is too high to ignore or eliminate or live with it. Another way is that to try to eliminate that damage mechanism, or if you cannot eliminate the damage mechanism or the probability of failure, then you try to mitigate, eliminate the consequence of it. For example, if there is a leak, if there is a surge in compressor, for example, then there is a trip speed. So before it goes to damaging the compressor because of some surprises, very high pressure, then there is a trip where it shut down the compressor. So sort of you eliminate them. If you cannot eliminate them, then you try to mitigate it. Mitigate in the sense that you got a storage tank, and you're trying to everything so it doesn't leak the storage tank. So once it corrodes or for any reason it doesn't leak. So for example, you put air vent on the top, so the gases on the top, because they could be very flammable and with any spark. So you are actually relieving the gases from the storage tank. Or if there is a leak, you put a dike around or a wall around the storage tank. So that is a secondary line of defense. So you put this, so the consequence is not that much. So by the time the whole fluid does not leak, or you use a double bottom tank, if one leaks, the other one can still hold on. You put some sensors. So all sorts of things. Or for example, if you expect a explosion in case of, a leak or a failure, then you put either a firewall curtain, water curtain, firefighting equipment, or you put a blast wall where it doesn't affect, you're mitigating the risk of fatality or damaging other equipment. Then you might also do a repair or replacement or alteration. Like alteration could be you reinforce it, or you try, for example, if you got a lot of corrosion, internal corrosion, so you do a weld overlay on carbon steel assets. So I'm just giving you some example how this monitoring, eliminate, mitigate, repair, replacement, alteration works. Monitoring, you can do visual external inspection, you can do periodic thickness measurement, you can put some sensors, temperature, pressure gauge sensors, and the flag off if there is anything going wrong. So these are all sort of monitoring. Focus on risk management from inspection point of view as a direct approach, and procurement process control as an indirect approach. So the first thing is, obviously this is a risk-based inspection, so the inspection is the main topic here. And there could be also some indirect approach. For example, recommend changing the process control to avoid or minimize certain expected damage mechanism. Recommend adding inhibitors, so it doesn't happen in first place, that particular damage mechanism. Consult with operation, maintenance, piping engineer, corrosion specialist, and other relevant personnel to explore any other risk mitigation activities. And then reassessment. So RBI is a live document, and therefore when new reports or information such as inspection, examination, testing, operation, and maintenance reports, tips off from operators come in, RBI assessment need to be reviewed to check whether the new findings affect the initial RBI inputs assumption or not. So if that is the case, then you need an assessment, reassessment. Anyway, RBI requires you to do a reassessment every 10 years if the next inspection interval is beyond 10 years. So, or any inspection report finding coming in between external, any observation, so you need to assess it. Or there is a change of process, or your initial assumption here changed, so you have to reassess to see how that affects your RBI assessment. Because corrosion and damage is a dynamic phenomena. They might combine with other damage mechanisms, and they might actually come up with a new damage mechanism. For example, chloride cracking, or you got then stress corrosion cracking, and then you got chloride stress corrosion cracking. So it might be two damage mechanisms coming, and deciding damage mechanism is chloride stress corrosion cracking. So, or the damage mechanism might change into a different version. Responsibilities and training. RBI philosophy, approach, and methodology shall be understood by all the relevant parties, and since there shall be a division of roles and responsibility between the key players, such as inspector, examiner, operator, maintenance personnel, owner, user. Also training and qualification of personnel involved shall be documented. There is a chapter exclusively about the key people, the relevant people, key players on this RBI, because it's not a one-man job. It's a team actually who is setting the scope and identifying the equipment, and then identifying risk drivers. You might need a process control specialist, you need a corrosion specialist, you need a vessel engineer, or a piping engineer, or a storage tank engineer to be available. And then the data should be analyzed, and then data should be gathered, and there is a management who does the budget, and RBI is also time-based. It's not forever. So you, based on the budget and the time set out, the level of the detail is chalked out. I mean, obviously, it all depends what is the risk from the client's perspective. So everybody should know where they fit in the puzzle, and RBI must be documented so we know what was the underlying reason for its recommendation and whether those assumptions and data inputs have changed over time and warrants a reassessment. Risk-based inspection program should be based on methodology. This is to have a repeatability, consistency when planning for risk mitigation and risk management, as well as to be able to compare numbers and figures. So even the software you are using, it should be the same software, because the logic's different for RBI. So the methodology should be constant when you are comparing two assessments against one another, because the parameters might have been different, the units might have been different. So it should be similar assumptions and similar methodology. Ultimately, RBI should correlate the risk with inspection efforts. Thus, inspection and examination testing is aligned with the expected damage, location, size, and type. So one of the key advantage of RBI is to focusing on damage mechanism that eventually lead to failure. And once how good we can find the damage mechanism, I mean how right we were, that is crucial, because based on what we assume is the damage mechanism, the dominant, we select the NDE tools, and so we know where we should look for it on that damage mechanism. For example, on elbows, on when there is a change of shape, is it corrosion under insulation? So it's very important that our assumptions are correct, because all our decisions and our effort will be diverted based on our damage mechanism. So it's very important that we do a data validation here.